So quiz on Friday, right? It's 4 questions, yes. 4.2, 4.3, 4.3, 4.6. So for 4.2, I like on the review packet, number page 3, number 2, right? For 4.3 first derivative test, I like page 4, number 2, and page 5, number 2. For 4.3 second derivative test, right, I said page 6, number 2, and page 7, number 2. Yeah, everything's number 2. And then finally 4.6, which is optimization, page 9, number 2. So, like I said, if you can do all of those, you can. What am I going to do under your quiz? I'm going to change the functions. That's it. I'm going to change the function. But I'm not going to give you some function you've never taken the derivative of before. That's the thing. Is you're seeing these functions over and over, right? And I like to do something like this function will be first derivative test on the quiz, but I'll put that same function, hey, on the second derivative part on the test, right? Just to make sure. Welcome. You okay? We'll just pull you all. You stay in that chair for the rest of the day. We'll get someone to pull you to the next class. Push you, right? So this is our chapter 4 review that I gave out. Okay, we're set? Nice. Let's do the new stuff. So we're talking about related rates here. Not on the quiz, but on the test, right? You with me? Not on the quiz, but on the test. So this is our last section of chapter 4 that'll be on the test. There won't be any antiderivatives on the test. That will be on chapter 5 test, okay? But let's start teaching 4.8. One, because I have to teach it anyway. And it's easy, right? It's pretty easy. So anyway, here are related rates. This is section 4.1. And the key here is you're doing all your derivatives with respect to time. So d dt is the new operator. And so d dt of x is just going to be dx dt. So we used to do d dx and we would get 1, correct? Right, you with me there? And do you kind of see the 1 as dx over dx? Do you see it? It's kind of not that way, but it's a nice way to think about it. It's an easier way to think about it. But so when we do all our derivatives now, there'll only be implicits. And instead of writing y prime, so if I do d dt of y, we're not going to call it y prime, because y prime is hinting that the independent variable is x. So we want to keep it, and this is Leibniz notation, we want to keep it as dy dt. Right? Yeah, so on the left-hand side, I'm saying, hey, take the derivative of y with respect to t, and then on the right-hand side, I make it look like one kind of unit. one variable, dy dt. So ddt is our new operator. We're always thinking implicit here, okay? Always thinking implicit. So every single variable will be differentiated implicitly, right? So what do I mean there? I mean ddt of x squared is what? Morning. What's ddt of x squared? Well, is there a 2x involved? And does anyone have the gut instinct that there's a 2x involved? Yes. So 2 times x times what, though? What's my implicit piece? dx dt. It's almost like saying x prime, right? But we're going to keep everything as this implicit with respect to t. Yes, Calista?
So you derived the word in the parentheses and then just multiplied by 4. Or
Yes, but remember what this is. This is the derivative of the inside function, right? We know the outside function is a square function. We know the derivative of the square function is 2x, right? But then I still have to take care of the inside function with respect to t. So we would usually say x prime, but we're going to use dx dt. It's just this new notation. It's not really new, but that's right. This is why this part is a little bit confusing. But you'll get used to it as you practice. So let me do a problem, right? I'm going to do a couple of examples, and then I'll show you which problems I want you to practice from the chapter. I've got a spherical balloon, believe it or not. So I'm gonna write out kind of a process in a second, but let's just do a problem right away so you see what's going on, okay? So this is an example here, right? We are going to inflate a balloon How do you spell balloon? Is that right? That looks weird. It is right. That has the shape of a sphere, like a globe of the Earth, right? And math classes. We don't have all the variables right. We simplify things. Can you ever imagine a balloon being blown up to be a perfect sphere? Think of the beach ball, right? Is the beach ball a perfect sphere? No, it's all those panels kind of glued together. You know what I mean? But we're assuming it's going to be a perfect sphere for sake of making the math easier. Okay, you with me? Yep. So. And we're gonna make the volume increase. So meaning you can see the thing filling up at a certain rate, right? So we want the volume to increase at a rate of 100 centimeters cubed per second. So the volume should increase at 100 centimeters cubed per second. And why is it centimeters cubed? Because the volume is 3 dimensions, right? Yes? We're thinking of length, width, or depth and height, right, to get a volume, right? So what is this saying? The volume is changing with respect to time, so that means dV dt is 100 centimeters cubed per second. So they're giving us the derivative value, right? And of course, I'm assuming that it's an auto air pump kind of thing. It's not like me pressing something with my foot, like a bike pump or something. It's got to be constant rate of change, right? Does that make sense? So it's not like going up and then stopping and then going up, right? It's just constantly going up at that same rate. At that same time, what else is changing? At the same time, what else is changing? If the volume of that balloon is changing, what else is changing? Say again? The surface area of the balloon, right? What else? Basketball. Just think of a basketball. What other geometry is involved? Soccer ball, sorry, Lana. Soccer ball, right? What else is there? Surface area, right? What else? Circumference is changing, diameter is changing, radius is changing. Right? Yes, you with me? So, we want to find how fast the radius is changing when the diameter is 50 centimeters. Find dr dt when the diameter is 50 centimeters. So I'm saying this thing is changing, right? In fact, it's going to go past a diameter of 50 centimeters at some time. This is way past 50 centimeters for a diameter. Okay, can you see the balloon? Right? So this is way past 50 centimeters. But I want to know exactly at that moment when it hits 50 centimeters, what is the radius? How is the radius changing? Yes, you with me? Good. So what do we need to do this? We obviously need a way to find dv dt, which we have, and dr dt. What were you going to say, Abigail? Yes. When the diameter is 50 centimeters, we know the radius will be 25 centimeters. Yes. But remember, well, we need an equation. What do we need the equation for? Does anybody know? The volume. We need the equation of the volume of a sphere. If I give you a problem that has geometry that we don't know from, like, I don't know, middle school, I will give you the geometry. Okay? So in this particular case, our volume is 4/3 pi r cubed. So it looks like we have a lot more variables than we want. And so that's part of the difficulty in this section. Hey. Hey, Ben? Oh, yeah. Yes, please, thank you. I can just show you what's going on. You see this is my second one already. You see the
Oh, yeah.
it's like the glue. You can
Looks
see the
like
glue.
The battery's bulging. Yeah.
Oh yeah, you're right.
Yeah.
That's crazy.
The battery's bulging. Yeah. All right.
I use it every day. I can't live without it.
This isn't a Dell product, so unfortunately we don't work with Dell on this because it's not a Dell product. But so most likely we'll just get it replaced for you.
That's fine.
So I'll send you instructions on how to do that.
Thank you.
So I don't interrupt your class.
Thanks a lot. I
All right.
appreciate it.
No problem.
Hey, Lauren. So it looks like we have more than we need, right? dv/dt, of course, I'm going to get that when I take a derivative, right? You see it? Diameter is 50 centimeters, but I really want r. So it's easy. When the diameter is 50 centimeters, r is 25. So there will be some little tricky thing that you have to think about in there sometime, okay? But be patient, draw a picture, right? So now what are we going to do? We're going to do the derivative, right? You with me? if I think you don't know it, I will give it to you. So this one I wouldn't expect you to know. And we will at times in bio pretend that cells are spheres. So because we'll be looking at structure of cells kind of thing and how they're changing, and it'll be easier to make them spheres, right? So you'll see this volume again in bio for sure. So let's do our derivative here. So I'm doing d dt of both sides, right? So d dt of the volume should equal d dt of 4/3 pi r cubed. Left-hand side is simple, yes? It's just dv dt. Or like v prime, yes? You with me there? But we're using this Leibniz notation. What do I get on the right side? Well, 4/3 and pi are constants, correct? They're numbers. So they go along for the ride. What happens to r cubed? 3 times r squared. And then what's my derivative of the inside is dr dt. Right? So we okay here? That's not a difficult derivative, am I right? It's easy compared to some of the things we have been taking the derivative of. But the whole idea, go ahead. So, it's the derivative with respect to time. So how is the volume, right? You can see it. The volume is changing at a certain rate. You can imagine the radius inside the balloon also changing, right? What's interesting to think about is the radius change speeding up or slowing down or staying constant? That's the interesting thought here. Right? When I'm walking away from a light, and you can see my shadow, right? Can you visualize that? When there's a street light and I'm walking away, you can see my shadow and it's getting longer and longer and longer and longer, right? Is it speeding up or is it slowing down? That's the interesting question. Be careful when you're thinking about that, because you could step off the curb or hurt yourself. So now I know this, right? I know this. It's 100. Question. Autumn.
You're only multiplying by
Yes, and I'm multiplying by this. Yes.
why?
Because it's how the radius. So I'm taking the derivative of this. 4/3 pi is constant. The derivative of r cubed is 3r squared. Derivative of the inside is how the radius is changing dr dt. Yeah, it's changeable. Sure, changeable. Now, remember what I'm solving for. How is the radius changing, right? How is the radius changing? Yes, you with me? I'm asking what is dr dt? So look at dr dt must be dv dt over 4 pi r squared, right? You see the 3's cancel over here? Yes, you with me there? And I know diameter, the point I'm interested, the diameter is 50 centimeters, right? So that means the radius is 25 centimeters. So I get dr dt. You ready? Dr dt is 100, right? Remember, my volume was 100 centimeter cubed per second, yes? Divided by 4 pi times 25 squared. So that looks like 1 over 25 pi. Is that true? Do we agree with that? And that is centimeters per second. I'm not a strict units kind of teacher your science teachers are probably really, really strict with units because they have to be. We don't, mathematicians don't. I already know if the volume is centimeters cubed, right, then a radius is centimeters. Yes? So I know the units at the end. I don't have to keep writing the units. But, yeah. Yeah.
Are you using the range?
Yeah, I do. So I'm solving for DRDT. So I divided by the 4/3 pi 3r squared. That's why it went down underneath. Okay. Because it canceled. 4 over 3 and 3. Oh, yep. Uh, 4, 100 over 4, 25, 1 to 25 cubed. But you do your arithmetic as you will. I do mine as I do mine in my head, right? Sometimes I make a mistake, but I didn't on this one. But again, don't worry about how I'm doing arithmetic. You're already done with arithmetic. You know how to do it. So do it as you want, right? All right, what decimal is this about? 1 divided by 25 divided by pi. So about 0.013. So, but what I'm really interested in is the radius slowing down or speeding up. Is the change in the radius slowing down or speeding up? What's your gut say? Or staying the same? Who says speeding up? Is the change in the radius speeding up? As I blow up the balloon at a constant rate, is the radius getting bigger and faster, or is it getting bigger and slower, slowing down, or is it going at the same rate every moment? What do you think?
Should be slowing down because smaller amounts of additional radius are needed to
I-
get the same amount.
I agree. That's my gut thought too. That the radius should be slowing down. The change in the speed of the radius as the balloon is blowing up, right? It seems to me it should slow down, but I don't want to go with my gut. I want to go with the math. So what should I check? I should check dRdt again, but when the diameter is bigger. So let's do when the diameter is 100 centimeters. So now what's my radius? 50 centimeters, correct? And what's dRdt now? So it's still 100 divided by 4 times pi times 50 squared. Yes, question? Got him. Say it again? Yes. Yeah, the first red, yes? Yeah. Yes, inverse relationship, exactly. Inverse relationship, yes. Correct, but I want to. You're right. We know those variables are inverse in an inverse relationship. So as one increases, the other decreases, right? So, but it's. I agree. It's obvious, right? So what do I have here? 1 over what now? Help me. 4 times 200 pi. No. Oh, no, you're right, 100. 2, yes, 1 over 100 pi. And what's that decimal? 1? Yes. right? So, what, do you see it? The sphere is still going at the same rate the whole time, right? It's being blown up at the constant rate of 100 centimeters cubed per second. At one point, when we stopped in a moment in time, like a speed camera, right? You know, we got that the rate was like 0.013 centimeters per second. Later on, we stopped again, speed camera, and we got it was 0.003 centimeters per second. So the change in the radius is slowing down. Cool, let's do my favorite problem of all time. It's one on every test. There's so last semester's test, there's no related rates on it. Because it was a summer class, it's too tough. Summer classes are pretty damn tough. You're all in a real good spot. My engineers in here are in a real good spot because Calc 1 in fall, Calc 2 in spring, Calc 3 in summer is the easiest math class to take in the summer. So the engineers, Calc 3 in the summer, please. I mean, unless you're in no rush, which is great too, right? If you're in no rush, you only want to take classes in fall and spring and summer work, right? Lots of people do that. But if you're going to take one class in the summer, Calc 3 is the one for you. My computer scientists, who are the computer scientists? So Calc 1 in fall, Calc 2 in spring, if possible, discrete structures in the summer. It's an easy class. It's basically how do you prove things. So I'd rather that in the summer rather than linear algebra in the summer, okay? This is just my opinion. So my computer science students here have to take Calc 1, Calc 2, discrete structures, and linear algebra, right? So if it's offered in the summer, it's offered on Rockville campus with Dr. Lee, Dr. Jason Lee. And he's great. So that's good. My bio students don't care about anything. Chem, where's my chem student? Who's chem in here? No one? Chem, you're done after Calc 2. Bio done after Calc 2. Chem, pretty much you need Calc 2. Bio, you need it depending on where you're going to university. Okay? All right, here's my favorite problem of all time. I guess should I do a step-by-step first? Yeah, okay. Read the problem. We're funny, us humans. We don't like to read too much. But we gotta read these problems. It sucks, but they're word problems, no way around it. Right? Take note of the given information. Most likely, draw a picture, right? Draw a picture that is like the skeleton of what's going on, right? So, like for the sphere, it's hard to draw a sphere, but right? And we had a diameter, right? A radius kind of thing. It's weird to try and draw a sphere, but I'm thinking about, obviously I have surface area, I have volume, I have a radius, I have a diameter, and I'm reading the problem, seeing what they gave me. most of the time they're going to give you an equation right? They're going to give you an equation and they're going to ask you to find some other variable, right? So in the problem that we got, we had 1 centimeter cubed per second, right? Is the volume. There's my equation, right? Find a function of one or more variables if most of the time I'm going to have 2 variables, but it could give me a function of 3 variables, like the one I had a diameter involved, right? So you'll have to do some kind of substitution there to get it to 2 variables, right? So find a function of 2 variables So 2 variables is what we want, because we're going to know how one changes, and we have to find the other. Step 5, take the derivative. Right, with respect to t, or with respect to time, right? That's my d dt, right, operator. Solve for the missing rate. I don't care if you plug the numbers in and then solve, or solve for the missing rate and then plug the numbers in. It doesn't matter. So you remember what I did in my problem, that first problem, right? I solve for dRdt, right? You see it? I solve for dRdt. I don't care if you do that or plug the numbers in first and then solve for dRdt, right? So meaning I could have plugged in the R value here of 25 and then solve for dRdt. Right? Is that making sense? Yeah. Sometimes it's so much easier to solve it algebraically before you plug in, but maybe do both until you know you're for sure you're doing things right. All right, here we go. Next problem. We got our step by step. Again, this is not on the quiz on Friday, okay? But there'll be one problem on the test, most likely with the ladder. So this is the sliding ladder problem. Wonder if I have a ruler in here. Do I have a ruler anywhere? Anybody have a ruler? A book would work.
Are you trying to make a tree line?
No, I'm just trying to show you what's going on with the ladder. So I'm going to just try it with a book. I think it'll work. So here's my book leaning against the neighbor. Everybody see it? I mean, you know what's happening. I'm just going to start to edge out the base, right? And then, right? You see it? Like the ladder sliding down the wall, staying in contact with the wall, sliding on the floor at the same time, right? Is it speeding up or slowing down? Speeding up for sure, right? Right, I start to get it to, once it gets to slide, right? You can see it's definitely going to speed up, right? So, I got a 10-foot ladder. Leans against the wall. Right? There's my 10-foot ladder. I don't really care about it looking like a ladder, but it can, right? But you see what I'm really looking at here? What's the math involved in this picture? A right triangle, right? So we know the height is y and the base is x, right? And I'm sorry, I drew it backward. Let me redraw it. I want it over here because I want x to be in the positive direction. So you can see this ladder sliding out. Don't look at this one, look at this one. Right? You can see this ladder sliding away from the wall at the base, and the top is sliding down. Right? Yes? You with me? So since the height is moving down, that change will be negative. It just means direction. And the x is sliding out, that will be positive. So dy dt will be negative here. Dx dt will be positive. So it says, when this ladder is 6 feet from the base, so obviously it could start leaning totally against the wall, or it could start leaning just a foot away from the wall with the base, or 2 feet away from it. At the end, it's 10 feet. The base is 10 feet, right? Because the ladder's 10 feet, right? So we want to know how fast is the base. What do we know? Yeah, no, how fast is the ladder sliding down when the base is right at 6 feet away? So find dy dt when x equals 6 feet and dx dt is 1 foot per second. Right, so the base is sliding out right at 6 feet. I did my speed camera and I found that it was moving at 1 foot per second at that exact moment. We know the base is getting faster and faster, right? As it's sliding, but we're saying at that one moment, exactly when the ladder is 6 feet away at the base from the wall, the rate that it's moving away from the base is 1 foot per second. We want to find how fast the top is moving at that moment. All right, what do we need? So we got all our information. Everything I wrote down was said in the problem. The picture was even in the problem, but obviously we know it's leaning as like a right triangle, right? So what's our equation that we need? What's the equation? Anybody got the big brain on today? So I want to get a function to be able to take the derivative of, right? Yes, Calista. Exactly. X squared plus y squared equals 10 feet squared. Again, I already know that my units, right? I already know the units all canceled here. So I don't bother putting them in, right? X is in feet, Y is in feet, the ladder is 10 feet. So there's all units got canceled out here. I just divided by whatever unit I had, right? So, but I'm ready to do what? Exactly. So I'm going to do d dt of this. what do I get? Beautiful. Plus 2y times dy dt. Remember, with respect to time. Yep. Equals what? Nice. Beautiful. Look at all the variables I have. I have an x. I have a dx dt. Oops. Sorry. I have a y. I have a dy dt. I have 4 variables. But I know x is 6, right? I want to know what's happening to dy dt when x is 6. So I'm going to solve this for dy dt. And that's going to be equal to negative 2x dx dt. I just moved that to the other side, right? Divided by 2y. I moved this to the left, became negative, and divided by 2y. Yes, we agree? So there's my nice version of dy dt, which is what I'm solving for. What do I know? I know dx dt is 1 foot per second. I know x is 6. What don't I know? Y. So I usually can find that variable going back to the original problem, back to my original picture. When x is 6, I don't know why, but I do. Oh, I don't know why, but I know 10 and 6. I know 2 sides, right? So 6 squared plus y squared equals 10 squared. 36 plus y squared equals 100. Y squared equals 64. So y must be 8. Yes? And again, after I do my math, I put my units back in. Right? So I know x is 6 feet. I know y is 8 feet. I know dx dt is 1 foot per second. And I plug in. Oh, did I do that wrong? No, 3/4, right?
So 1 second for the distance.
Yes. Why is it negative? Because the top of the ladder is moving down, right? Yeah.
What is that under?
It means as this ladder sliding away from the wall, and we know it's getting faster. At the very moment that it's 6 feet away from the wall, we're finding out the speed of this thing moving down. So the base of the ladder is sliding away at a certain speed. The top of the ladder is sliding down the wall at a certain speed. It's not. Well, think about it. Think about it. It's a 10-foot ladder, right? So it could be 1 foot away, 2 foot away, 3 foot, in between. It could be 5 feet away, right? If you think about it, there probably is an equilibrium point where both x and y are moving at the same speed but in opposite directions. Where do you think it is? X equals what? If you had a guess, 5. Because then the base and the height are exactly the same distance. So, but they're asking at 6 feet. -6 to the left. Right? So think about it, I'm walking away from the light. Can you see your shadow getting longer and longer in front of you, right? And so obviously I'm going to be walking at the same pace as I normally do because I'm slow. But looks like my shadow's getting faster, like it's running away from me, right? So that's all we're looking at. As one thing is changing, what's happening to
So
something
the
else?
given is the bottom slightly away as the
Exactly.
kind of by
Exactly.
the box.
Exactly. What else is changing when this ladder is sliding? Yes, the height. That was our DYDT, right? What else is changing? The angle's changing, right? So how would I find a d theta dt here? D theta dt. Look at that picture, right? What do you see? Yes, you could do a cosine, but there's a better trig because I have x and y, tangent, right? So tangent of theta equals y over x, derivative of both sides with respect to t. Yes? What would we get? Well, on the left side, it's just a trig, right? So derivative of tangent is secant squared, right? So secant squared theta times d theta dt, right? Chain rule. And on the right side, it has to be quotient rule, right? So y dy dt, x dx dt over x squared, right? So what do I get? I get x dy dt minus y dx dt all over x squared. Don't be surprised if I do that one on your test. What else is changing in this triangle? What else is changing? What else is changing? What can you tell me geometry-wise about a triangle? Say again? Yes, more. Something else. Perimeter? Perimeter? Sure, right? X plus y plus 10 is going to equal the perimeter, right? What else? That's a boring one, so I won't ask that one. Area. What's my area of this triangle? So this one is theta is changing, right? Let's do the nice area equals xy over 2. So I need a product rule there, right? Everyone agree with that? Half the base times the height, right? Or better yet, 2a equals xy, right? That makes it a little bit easier. Let's do that derivative. What do I get on the left? DADT, A prime, if you will, right? But we're going to use the Leibniz notation, so we are assuring ourselves that we're taking the derivative with respect to time. So 2 times dA dt has to be a product rule on this side, right? X dx dt, y dy dt. So I get x dy dt plus y dx dt. Notice all of them, right? All of them have x's and y's involved. Where do I get my secant squared theta from? Yes, but where I want it all to be in terms of x and y. Remember, because I found I said x was 6. I said y was 8, right? You found that. I know dx dt is 1 foot per second. I know dy dt is negative 3/4 foot per second. So I know everything on the right side there. I know everything on the right side here, right? But I don't know secant squared. Where am I going to get it from? The triangle, right? I just go back to the triangle and get the ratio for secant and square it. Yes, I got mad scroll skills. Where do you need me? All right, problems. I guess up to 25 is good. I'm not assigning any more homework. Friday's our last quiz. So no more homework, no more quizzes after Friday. We will have a chapter 4 test next Friday, a chapter 5 test December 2nd, and a final exam. The final exam, and we're going to review a whole week for the final exam. So because I'm teaching chapter 5 up until that full first week of December, which is final exam review week for me. Some other teachers might still be teaching, but I'm not. I have 3 classes, Monday, Wednesday, Friday. I will review chapter 2, chapter 3, chapter 4 on each day, right? Chapter 2 one day, chapter 3 one day, chapter 4 one day. I won't review 5 because we'll just have done it, right? Does that make sense? So, what did I say, 1 to 25? Suggested problems 1 to 25, yes? But I really like a few problems. Yep. They're up there. Yeah, so let's just make sure. Stupid login system. So Blackboard. All right, there's one click. I hate this. courses to semester 3, our class 4, and on the sidebar you should see homework solutions, right? So chapter 4 and 5, it's all up there. Yeah. Over the winter, make sure you download these. You're going to Calc 2 over the winter. Review chapter 3 and chapter 5. Okay, be ready for Calc 2 by reviewing chapter 3, chapter 5. Chapter 5 for us in Calc 1 is up to 5.6. So, and then you'll finish chapter 5 in Calc 2. Okay. I mean, the first 15 problems are all easy, but then I like the ones, I like the ladder problems. Are there any ladder problems? There are no ladder problems. What happened to those ladder problems? Damn it. Well, do the ones on my old test anyway. Oh, number 40 is a ladder problem. They changed the book. It's okay. Nice. One last thing to do in 4.8, okay? So we have our checklist for integrating. And so if you haven't realized yet, integrating is the same as antiderivative. Integration is the same as finding an antiderivative. Okay? We're going to change the notation next week. But for now, we're just going to say, I'm going to give you y prime. You're going to give me y, right? You're going to give me the original function. So our first step was, I know y just looking at y prime. Right, so y prime is 1 over 2 square roots of x. Gives me y equals what? Square root of x plus that constant of integration. Second step was the power rule. When I do a derivative with for a power rule, I take the exponent and make it the coefficient and reduce the exponent by 1. To do that to do that backward, right? So y prime is x to the n. Y is x to the n plus 1 over n plus 1 plus c. So I'm adding 1 to the exponent and dividing by the new exponent. Those were the two that we did last class, right? And step 3 is it's tricks. And I might add to this a little bit, but I can long divide. I can multiply by 1. I can add 0. I can divide and conquer. And maybe more, I might add to them a little bit, but we'll do one like that now. So these are our integration methods, right? And what did I say? What did I like in 4.8? Did I give you suggested problems there? I don't think I did. Let me give you suggested problems in 4.8. Number 1 to 49. So let me show you one of these, right? Um, so y prime is x squared over 1 plus x squared. So I'm going to add 0 and then divide and conquer. I'm going to do 2 tricks in one with this one. Anybody recognize this one? You recognize y from here? You see anything that looks like that would give you some kind of y? Do you see any kind of take a derivative of something and get something like this? Yeah, what? Arctan. So I'm going to divide and conquer. I'm going to add 0, divide and conquer. And you're saying to me, well, when do I know to do enough problems? And you'll see all the tricky ones up here. Okay? I could long divide but with this one too. Do you see why I can long divide here? Upstairs mother function is x squared. Downstairs mother function is x squared. So I can divide this one. In fact, whenever I have a leading polynomial that's higher or equal to the leading polynomial term in the denominator, I can long divide. And should. But I'm going to divide and conquer. So I've got x squared over 1 plus x squared. And I'm going to add 1 and subtract 1. So still equal, yes? You agree? Still equal? Yeah? Yep. Divide and conquer. I can take anytime I have a multi-term numerator, I can split it. So I've got y prime as x squared plus 1 over 1 plus x squared, and then minus 1 over 1 plus x squared. What's the first part of this? In green here, what's that first part? 1. So 1 minus 1 over 1 plus x squared. And now these are both back to step 1. You should recognize. What did I take a derivative of to get 1? Hello? X, thank you. What did I take a derivative of to get 1 over 1 plus x squared? We said it before. Arctan of x, right? And then plus a constant c. So we'll see those kind of steps happen a lot. Divide and conquer happens quite a bit, where you have multi-term numerator and you pick the ones you want over the denominator and the rest of them over the denominator. By the way, if I long divide there, what do I get? I get x squared plus 1 into x squared, right? So I get 1, and I get x squared plus 1, and then I change the signs and add. So you see I get the same thing as when I added 0 and divide and conquer. Yes, Sheila? How did I get my y equal? Yeah, so derivative of x is 1. Right? So I'm back to, you'll see, and this will happen when we start doing these problems. Remember, I have a 12-step list coming. 9 more steps to go. What happens is you try this, doesn't work, try that, doesn't work, try that, doesn't work. You try this, it works, and then it pushes you back to a different level, and then you're doing the same thing again. And finally, it will get you to something you know how to integrate just because you know the derivative, right? So,
Why don't we just put arc tan with the first
because,
and like have like
sure, so let's go back to y equals arctan of x, right? We know y prime is u prime over 1 plus u squared, so 1 over 1 plus x squared. So we didn't have that.
but it's like the X is different.
Yeah, again, you gotta think. You gotta try things. They get pretty nasty. By the time we're done with chapter 5 and calc 2, they're really, really complicated. But you have the intelligence, you have the skills. If you can differentiate, you can integrate. Of course, the hard part is when we start undoing the chain rule. That's the tough part, right? Remember, we learned to differentiate, and then you had to do the derivative of the outside, and then times the derivative of the inside. So when we're undoing that, it gets pretty crazy. Nice. Have a great day.